Okay, so we're going to move on to chapter 11. You got homework due tonight for chapter 10. We covered that last Wednesday, so we're not going to talk about that. We're going to move on to chapter 11. And then the homework for this will open up at 9 a.m. You can start working on it. It'll be due Sunday like normal, okay? Okay, so far we've been talking about things like, we're looking at trying to figure out what the population mean is for a given samples, right? And so population means there's things like, like the mean wingspan of a certain type of bird, or the mean waiting time at a coffee shop, or the mean weight of basketball players or something like that. So this is a different kind of statistic called population proportion. So the idea here is each member of a population either has or doesn't have a specified attribute. Okay? So the population proportion is the proportion or percentage of the entire population that has the specified attribute. So just P means the percentage of items in the population that has the attribute. P hat, this is called P hat. So P hat means the percentage or the proportion in the sample. Okay? So just P is the proportion of the entire population that has the attribute. P hat is the proportion of a sample that we take. Okay, so let's just practice that. 72% of 125 adults polled prefer vanilla over chocolate ice cream. So 0.72. Is that a value of P or is that a value of P hat? So 72% would be 0.72. Is that a value of P or a value of P hat? Okay, I have one vote for P hat. What do you think? People are nodding. That's right, because this is a proportion of a sample. So that would be a P hat. All right. 56% of all cars in the U.S. are imports. And so that would be 0.56. Is that a P or a P hat? P. Okay, going back to this one. So now suppose I took another poll of a different 125 adults. Am I going to get 0.72 for P hat? Ashton says no. What do you guys think? Am I going to get, if I'm going to pull another 125 people, am I going to get 0.72? Maybe. Maybe not, right? So this is the idea of we could keep taking polls of 125 people and we would get different values. So one of these is a fixed value and one of them is variable. So P hat, is that variable or a fixed value? Variable, because you take a different sample of 125 and you get a different proportion. You get 0.71, then you get 0.74, then you get 0.68. You see? So this is a variable. But if you're talking about a population, so what percent of adults, all adults, prefer vanilla over chocolate ice cream, then that would be a fixed value, right? So it's some fixed value that we're trying to find, right? We want to know for the population. So this, if this is a true statement, then that's a fixed value, 0.56, doesn't change. Okay, so if this is a variable, then we can, just like we've seen before, we can look at the distribution of P hat. Okay, a sampling distribution, right? So it's a variable has a sampling distribution. Okay, so that's what we'll be looking at. So it's like we keep taking lots of polls of 125 adults, and then we take those values, and a distribution takes form, right? A distribution, just like we've seen before. We call sampling distribution, and this would be the sampling distribution of population or of sample proportions. Okay. Wow. It's a late day, I guess, you guys. All right, here we go. So, so then this right here, right? We talk about sampling distribution. So the mean. Don't try to just write all this down. Listen. So the mean of p hat equals a population proportion. So the mean here. This is sampling distribution. The mean of p hat. What does that mean? It means we take lots of samples and we get a p hat for each sample, and we're looking at the mean of those. And if we're able to take all the samples of size n, then the mean of that sampling distribution would be the population proportion. So this thing right here, what is this? This is the mean of p hat values. In the sampling distribution, right? And the mean of all those p hat values is going to be the sample proportion for the population. So very similar to what we had before, okay? The standard deviation is this. The standard deviation of that sampling distribution is this right here. So it would be the population proportion times 1 minus the population proportion over n and the square root of all that whole thing. What was it just for a regular sampling distribution? So before, what was this? What was sigma x bar? Remember?
Sigma.
Right. Hopefully you were thinking that. Sigma, the population standard deviation, over the square root of n, gave us the standard deviation of the sampling distribution of means of samples, right? But now we're looking at the sample proportion and looking at that distribution. Okay, and so we like this because we're nice and familiar with the normal distribution, right? So it's p hat, the p hat distribution is approximately normally distributed when n is large. Okay. So then we're going to, since it's normal, we can use our z-scores. Okay, so here are the assumptions. Okay, we have a simple random sample. Okay, and then here's the one condition we have to meet. The number of successes, okay, x is like, say in that previous example, how many people prefer, so you take a sample of n, x stands for how many people prefer vanilla over chocolate. And then n minus x would be everybody else, right? Both of those numbers have to be 5 or greater. So 5 people or more have to be in both categories, that they meet the condition and that they don't meet the condition. So what is that saying? It's saying that this sampling distribution breaks down if almost everybody is a success or almost everybody is a failure. It's got to be, there has to be away from the ends there. Okay, so more than 5 people, 5 or more, have to be what we call successes, and then 5 or more have to be non-successes. So if almost everybody's a success, then the math breaks down. Can't do it. Or if almost everybody's a failure, less than 5, less than 5 are successes, then it breaks down. Okay, but then everything else is the same. It's just now that we have a different way. This is the way of calculating the standard deviation for the sampling distribution of proportion. Okay, but it's the same thing as before. So our sample proportion is going to be our point estimate for the population proportion, and then we're going to go plus or minus our z-value times the standard deviation. So this is our standard deviation. We're going to go that many standard deviations below, and we're going to go that many standard deviations above, and that forms our confidence interval. So very similar to what we've done before, but we're just looking at a different kind of statistic. Okay, let's give it a try here. So we've got everything we need. So you can read this, get familiar with the problem here. Pass it back behind you.
Yeah.
Everybody got one? Name and date, please. Name and date. What's the date? 7? 6? Day 6? Okay, so it says, a Harris poll asked Americans whether states should be allowed to conduct random drug tests on elected officials. Of 21,355 respondents, 79% said yes. Okay, so first let's talk about how many respondents said yes. Could you figure out how many respondents said yes? So do that first. Could you do that? That's what we call X. That's what we call X. X is the number of what we call successes. I'm sorry? Oh, sure. All right, so how many said yes? So do that first. And then go ahead and do A and B. I think as long as you wrote down what that sigma is, p hat. Oh, wait. Let's do this together. Okay, so how would you get how many said yes? How do you take 79% of that? You should all know how to do that. Right, you're going to take 0.79 times this. Who's got it?
16,870.
Okay, 0.45? 0.45? You're all nodding. 0.45? No, these are people. These are people. Lots of blood, right? It's just 0.45. So, well, in this case, you would round it. You would round it. because it's not about like the size of the interval or anything. This is just the 79%. So if it's 0.45, then we'll just go with this. This you want 16,870. Okay, so now we want the margin of error for a 99% confidence interval. Okay, so we've got that. So we need the sampling distribution, right? So we've got a p hat of 0.79, and that becomes our point estimate for the confidence interval. So this is the best we know that the proportion is truly 0.79. We've just got this one. It's a big sample, but it's still a sample. So this is the best we know. So the center is going to be 0.79, and then we're going to go what? We're going to go up by z, whatever our z is, times z times standard deviation. So that standard deviation is what I was writing out before. It's going to be, we're going to do 0.79 times 1 minus 0.79 divided by n, and take the square root of that. So this is the standard deviation of the distribution of sample proportions. The proportion, that's standard deviation. Anybody got it? So this is 0.21. I'll make it go a little faster. Nice and loud as soon as you get it. 0.0028? 79? Let's do 79. Okay, and then we need what the z is. How are we going to get the z? We want a 99% confidence interval. So what are we going to look at if we want a 99% confidence interval? This is review. So we're going to take z of what? What would we be looking for? What? I'm drawing a blank. What's that called? The yeah, but what's that thing called? Not the critical value. That's what we're finding. But significance, right? Significance. What significance level will we have if we're doing a confidence interval with a margin of error 99%? .005, right? Because we want half of 1% out to the left, half of 1% out to the right. So our significance level will be 0.005. Or half of 1%. Tell me what the z value is. 2.575. Agree with that? Okay, so now you can build your confidence interval. So remember that our point estimate for the population proportion is the sample proportion, and then we're going to go this many standard deviations above that, and this many standard deviations below that, and then there's our standard deviation. So standard deviation is really small. Why? Because we got a huge sample, 21,000, huge sample. So we get a very, very small standard deviation. Okay, so we got our 0.79. And what's the upper limit? Anybody got that yet? .7971. Anybody else get that? We got one agreement? Two agreements. Okay. 0.7971. Okay, and then below? Sounds right. Okay, so we're 99% sure that it's between 78.3% and 79.7%, the actual population proportion. That's a really narrow, so why is it such a narrow margin? Why are we're 99% sure that it's in this very fine margin of percent, right? From 78.28% to 79.71%. How can we be that confident on that small of an interval? What's the key here? What's going on? Yeah. Yeah, it's such a huge sample size, right? The bigger your sample size, the more and more confident you can be that you're close to the actual population proportion. Does it make sense? So we can be 99% sure that between 78.28% and 79.71% of all people, what is this? Agree that states should be allowed to conduct random drug tests. Okay, what's the margin of error? Okay, so what's the margin of error? So it's not about a formula, it's about a principle, right? It's about an idea. What is the margin of error? What does it mean? Remember? Yeah, right. So our margin of error, so we're going to say that 79% of people approve of random drug testing with a margin of error of this. So how would you find that? A couple different ways. So there's a couple different ways. So the margin of error is how far away from our point estimate are we saying that we know it's less than that far away, or 99% confident it's within this distance of 0.79. So how could you, now that we've done all this math, there's two different ways you could talk about finding E. What's one of them? Yeah, so you could take either one of these. You could take, say, the upper limit and subtract 0.79. So it'd be E equals 0.0071 or 0.71%. So this poll has a margin of error of 0.71%, meaning we're 99% confident that our true population proportion is within 0.71% of 0.79, or within 0.71% of 79%. What's another way to get that number? So where else does that number come from besides subtracting the upper limit from the middle? Okay, so that's kind of the same thing. Yeah. So you could do that minus that, but I'm thinking of a different way entirely. It's actually how we got these numbers, right? It's actually how we were able to get these upper and lower limits. Which was what? What did you get? What did you do to get this number?
Multiply Z of over 2
Uh-huh.
by the root of by what is in the root.
Right. And so what does E have to do with that? So are you saying that's what E is?
That's how we get it.
Yeah, how did we get this number? What did we do? What did you punch? What calculation did you do to get this number? Okay, be specific. How did you find this number? Where did it come from? Yeah.
Sum of the question plus the Z plus Z of over 2.
Right?
Which got us 2.7575.
Okay, so if that's the case, then what is E? What was E in that calculation that you did?
0.0027.
That's that right there?
No, that times 2.57.
Right, so yeah, to get this number, didn't you take 0.79 plus something? Isn't that how you did it? Yeah, you had 0.79 and you added something to get this. Well, that's E, right? So whatever you add to this is get you here. All right, so it's this times this is what you added, right? We took this many standard deviations, and this was our standard deviation. Okay, so we took 2.575 of those, added to our point estimate to get that. So that is E. It's what you added to the point estimate to get the upper limit and what you subtracted to get the lower limit. How far you went from the middle. It should make sense. Should make sense. And then if you were given the upper limit and the point estimate, you would just subtract to find E. Okay, so why don't you try, so here, first you have to determine if it's appropriate or not. And what did we say? So x has to be 5 or more, and then n minus x has to be 5 or more. And if that's the case, if you have that, then you can use the 1 proportion z interval procedure. That's what we're doing. This is the 1 proportion z interval procedure. All right, well, we never talked about B, sorry. Is the margin of error larger or smaller for a 90% confidence interval? So why don't you talk about that and do that on your sheet. And you can talk amongst yourselves. And then I want you to do 11, 20, 21, and 22. And you have to check first whether the procedure is appropriate or not. Remember, so x has to be 5 or more, and also n minus x has to be 5 or more in order for you to proceed and do all this work. Okay, so I'll let you loose here. So you're going to do part B on your sheet, and then 11, 20 through 22. Yeah. Yeah. Uh-huh. Does everybody, most people agree with the numbers that we did here? Do you agree with this? Okay, so what were you? Okay. For when doing which part?
Every part I was going to do so.
This is under the square root, right?
Yeah.
This is
No, it wasn't. Okay, that's right.
That's under the square root. Yeah.
Okay. I knew I knew it was mine.
If you haven't finished that, 1120, write that down. X equals 40, n equals 50, 95%. Okay, keep going. 2 more. Let's add some. Okay, everyone feeling like you know what you're doing? Can we go on? Any questions?
How do you, how would you interpret, like, would you say you
No, you say you're not. We're 99% confident of what? You just say we're 99% confident that what? That's the interpretation. Okay to go on? Okay, so then the next part is hypothesis testing related to population proportion, which is, there's not a lot new here. So now that we understand population proportion, we know hypothesis testing, we're just doing hypothesis test on population proportion. So again, we need to have So we're going to have a null hypothesis that the population proportion is a certain value. Okay, we're saying we're going to say the population is a certain value, and then one of three alternative hypotheses, just like before. Either that population proportion is not the null value, it's less than, or it's greater than, just like we had before. Okay, so the condition now is that, so this is like what? This is like x, but it's a hypothetical x because it's based on our null hypothesis, right? So if we had, the proportion was 60%, then to get the hypothetical number of successes, we take n times 0.6, right? 0.6 of n, and then n times the result. And it's that same test as before. Hypothetically, we need 5 or greater successes and 5 or greater failures. Okay? But it's hypothetical because it's the null hypothesis value that we're using to calculate a quote-unquote number of successes. Okay? All right, then we have a significance level, and then we have our test statistic, which is the same as before. Remember, so before it was x bar minus our null hypothesis value for the population mean all over and now it's the same thing, but according to the population proportion standard deviation, which we just did with the confidence intervals. Okay, so everything is the same. It's just now we're applying the hypothesis test to this idea of finding population proportion. So let's do an example, and then I'll have you do one or two. Okay, and then the same thing, you can do critical value, you can do the critical value approach where you find the test statistic and the critical value and you compare those, or the p-value approach where you find the confidence or it's the same thing, the significance level versus your actual probability from your z-value, and you can compare those. Same thing as before. All right. So let's do 59, okay? Or let's do 63. So we have in 63, first we want to determine the sample proportion, decide whether the one proportion z-test is appropriate, and then if it's appropriate, perform this the specified hypothesis test. Okay, so in 63, x equals 16, n equals 20. Is it appropriate one proportion z-test? Is it appropriate or not? Remember, looking back here, so the hypothesis test is based on what? It's based on the null. So it's based on the what we're choosing for the null hypothesis. Okay, so we're going to look at n times p naught. So if we take, so hypothetically we're going to test against a null hypothesis of what? That the population proportion is 0.7. So then to see if the test is appropriate or not, we're going to take 0.7 of 20. And what's that? It's 14. And so we're going to, so that's kind of like so that's our hypothetical value of x. And we're going to look at what? 20 minus 14, which is 6. So this is like the hypothesis that we're testing would indicate a number of successes of 14 and a number of failures of 6. Is it appropriate to use the hypothesis test? Yeah, it's okay. Right? This was from our sample, so this is what we're going to compare it against. But it's based on the null hypothesis that we declare whether or not we can use the test or not. So yeah, we're good. All right, so here's our null and we want a significance level of 0.05. So we need our test statistic and our critical value. How do we get the test statistic? That's based on our sample, right? That's based on our sample. So how are we going to get our test statistic? That is z equals what? So how are we going to get that? So it's the same as calculating a z value for a confidence interval, right? We're going to have our test statistic is going to be okay, once again, it's going to be the what? It's going to be our sample. It's the difference between our sample proportion and our null hypothesized proportion over the standard deviation based on the null hypothesis. So this is important. So this is going to be our proportion from the sample, and it's distance away from our null hypothesis value, and then the standard deviation is going to be based on what? It's going to be based on the null. So that's key. So let's write that down. Test statistic is p hat minus p naught over okay, so our test statistic in this case, what is p hat? What is p hat, or the sample proportion in 1163? Was it? 0.8. It's going to be our 16 over 20, right? So we had 16 successes out of 20 in our sample. So we're going to have 0.8. Okay? Minus 0.7. So we're testing to see if there's evidence that the proportion is something different than 0.7, right? Over square root of 0.7 times 0.3 divided by 20. All of that square root. Once you get that value, say it nice and loud, and then see if we get confirmation on that. And this whole thing is in the square root, and that whole thing is in the denominator. 0.9759. Somebody else get that? That's 2. That's 9. Is that right? Okay, cool. All right, so that's our test statistic. What about critical value? A critical value comes from, remember, comes from the significance level 0.05. Okay, so what we're saying is and since we're doing a not equals hypothesis test, we've got 2 areas, right? So what is that area right there? Right? The total area for both tails is 2-tailed test. So the total area of both tails is 0.05. So we're going to have 0.025. So then you're looking at your table, and you're going to get the critical value. As soon as you get it, tell me what that is. 1.96. Agree? It's a familiar one, right? 1.96. So then if we're doing the critical value testing, we're comparing these two. And so are we going to reject or not reject the null hypothesis? This is 1.96, and then we'll have negative 1.96. And where do we fall here? So our kind of distance from this 0.7 is like 0.9 standard deviations, 0.98. Reject or no reject? Do not reject, right? We're like something like this. Here's our test value. That's in the non-rejection region. So we do have evidence or we don't have evidence? We don't have evidence of what? We don't have evidence that okay, what did you say? Yeah, we don't have evidence that the population proportion is something other than 70%, 0.7. Right? We don't have strong enough evidence to say that the population proportion is something ever other than 0.7. Does that make sense? So it's the same as before, right? Any questions on this example? So let's just do one, have you do one application problem. All right, let's try 68, this one. See if we can do this one for your sheet. Okay, try not to spin your wheels, get right off the starting block here. So I'll interpret for you. So the 9.8% is going to form our null hypothesis. Okay? So originally, we had 9.8% of U.S. families below the poverty level. So that's going to form the null. Okay? And then they selected 400 Wyoming families, 25 had incomes below the poverty level. So this is going, that right there is going to form our test statistic. And what are we testing? We're testing to see if, based on that sample, the poverty level is lower than this one. Okay, so you can have an H naught, HA, and the key is here to get your alternative. We want to know if based on this sample, are they below? So that's going to form your alternative. Can you do it in a couple minutes? So let's get that null and alternative hypothesis, and then you're going to find your test statistic and your critical value. Find your test statistic and your critical value, and compare. And I'll just come around and make sure you're on the right track. That's 98%.
So we got 9.8%, not 98%. I just looked at that. That's right.
Make sure you're on the right track here. That's the null and alternative. Check, make sure you got it.